So what we want to do today is kind of give you an introduction into some of the things you're going to be doing in Module 2, and in particular give you the necessary sort of fundamental background to be able to understand most of the key aspects of logic. So, in this lab, this is really one of my favorite labs because in my own research group, and really everything I think about as a chemist is really very much as a kineticist. So I really try to understand the kinetics or the rates by which molecules interconvert into each other. And that's fundamentally what we're going to actually study in this. And so there's a cast of characters that plays very prominently in this lecture and really in this lab, right? And these are, I would say, some of the father figures of inorganic coordination chemistry and kinetics. And one is Arrhenius. So how many have heard of the Arrhenius equation? Okay, great. This is the man to whom that namesake is given. He won the Nobel Prize in 1903 for his work on studying the kinetics of reactions, and really kind of very much laid the foundation for what we now modernly refer to as sort of transition state theory, though that was developed to a great extent by Henry Eyring and many others afterwards. The other character that plays a very, very big role is Alfred Werner. And some of you might have heard of the Werner complex. These are very, very prototypical classical coordination complexes. And it's really named after Werner because this was in a time when we didn't understand in the early 1900s about molecular orbitals or bonding or quantum mechanics was really very, very much in its infancy. And so Werner basically did very, very simple experiments to understand what are the ratios by which metal ions bind various molecules. And he found things like ammonia and water and other things would bind metal ions. And he could identify the stoichiometric ratios of these using classical chemistry techniques, and was from there actually able to build up an enormous amount of information about the very basics of how metals and ligands bond to each other. So this was really, really impressive work. It took quite a bit of time later where this person plays very, very prominently. This is my academic grandfather, Henry Tauby, and he did really foundational work in understanding the kinetics of charge transfer reaction, the kinetics of things like ligand exchange and electron transfer between metal centers. And I would say that the modern kinetics of how we think about metal-ligand bonding in coordination compounds in particular comes largely from Henry Tauby's contributions. In fact, the very lexicon that we use comes from his contributions. So some of you might have heard the term that a certain metal-ligand bond is labile or inert. So those terms, labile or inert, were coined by Henry Tauby to describe the relative rates of ligands exchanging between a metal center and a solution. And so his contributions really are everywhere in our contemporary understanding of the behavior of coordination compounds. So what do we really want to do here, right? So what we want to do is introduce some aspects of the synthesis of simple coordination compounds, particularly as it relates to the laboratory. I'm going to introduce a little bit of vibrational and UV visible spectroscopy, but the vibrational spectroscopy will be in terms of practical aspects. Marius will give a full lecture on that, I believe, next week. And the other thing is that we're going to explain a little bit about the ways in which you can probe the rates of substitution of ligands at a transition metal center and use that as a basis for understanding mechanisms. So let's begin very, very simply, right? So in general, when you have any two partners that are engaging in a reaction, the things that determine the rates of those reactions are primarily governed by the orbitals that are at play. And for transition metals, the principal orbitals that are at play at the frontier level, that is the highest occupied and the lowest unoccupied levels, tend to typically consist of the metal center d orbitals. And so there are 5 d orbitals, right? The xz, the yz, the xy, as well as the x squared minus y squared depicted here, as well as the dz squared and the x squared minus y squared orbital. So all of you are familiar with this. And you can understand how the bonding characteristics of, say, a very simple coordination compound, in fact, this is one of the prototypical Werner compounds. We've known about compounds like this for the better part of the last century, consists of basically an octahedron, right? An octahedron that consists of, in this case, ammonia ligands or amine ligands binding to a cobalt transition metal center. This cobalt is in the 2+ oxidation state, and since each of these ligands is neutral, that in net means that the oxidation state of the cobalt center is 2 because the overall charge is 2+. And we can think a lot about the bonding in these centers by understanding how the orbitals on the ligands interact with the metal center d orbital. So a question could be asked is, how will the ligands impact the energy of the orbital? So just take for a moment, I know all of you have been introduced to this in one form or another. If you can, consider for a moment how the d orbitals would be split due to bonding interactions with these ligands. So if I orient these ligands in this octahedral arrangement, and I've deliberately chosen to orient the axes along the axes that are in this Cartesian coordinate plane. There's a slight angle here, but imagine that x is pointing along the cobalt amine, and the y is pointing along one of the other bonds, and the z is pointing axially along the cobalt amine bond. If this were the case, which of these orbitals would be pointed, if you will, at the ligand? Which one has electron density that is directed at the position of the ligand? Yes, someone was going to say.
It looks like the top two.
Yeah, great. This is not a trick question, right? So we have an octahedral arrangement of ligands, and you can see that this orbital, right, has electron density that is quite literally poking out, if you will, in the direction of the equatorial for amine ligands here. Now this orbital doesn't have any electron density that's pointing at the two axial ligands, but this dz squared does. Right? And it also has a torus here, which is radially symmetrical, and therefore sort of points equally at all of the equatorial ligands. Right? And this, the key point I want to make is that for symmetry reasons, the interaction of these orbitals with these ligands is very different than the interaction of these orbitals with these ligands. In fact, if you look at the orbital density here, remember that the x-axis is actually pointed in between the lobes of electron density that comprise this xy orbital, as are the z-axes and the y-axis pointed in between the yz orbital and so forth for the xz as well, right? So all of the lobal density in these ligands is actually pointed in between, all of the lobal density in these d orbitals is pointed in between the amine ligands. As a result of that, the bonding interaction between these amines and these ligands is relatively negligible, right? Okay. So given what we know about this, we can start to assemble what we might anticipate to be the electronic structure of this transition metal complex. Right? And the first thing we have to realize is that before I impose any ligands on this cobalt center, all 5 of these orbitals are degenerate in energy. Right? And that just comes out of a quantum mechanical approximation of the cobalt center as having orbitals very analogous to that of the hydrogenic wave functions. Right? So the wave functions from quantum mechanics define these orbitals, but all of them are essentially the same energy if you're in an environment where no ligands are interacting. Right? If you just have a free cobalt ion, not in solution, because even in solution ligands are bound, but if I have it sort of in the gas phase, right, where nothing is bonding to it, in that environment I have all of these orbitals being degenerate, same energy. Now what we said earlier, right, is that the interaction of these 3 bottom orbitals, the xy, the xz, the yz, have lobal density that points in between these ligand orbitals. And as a result of that, we would expect them to not have a significant bonding interaction. As a result, their energy is not changed even when I introduce these ligands to the metal center. But what would we expect would happen to these metal center orbitals, or these orbitals here, upon interaction with the ligand? When I take any 2 molecules and I bring those orbitals together, what is usually the situation that occurs? What is the orbital picture that describes that bonding interaction? maybe not asking the question clearly, right? I have an orbital. Let's take a simple example, right? I have say, the orbital of a hydrogen atom and an orbital of another hydrogen atom, and I bring these two orbitals together. What are the resulting orbitals that will come out of this arrangement? Yeah. So you generate an in-phase combination of these orbitals that generates a bonding orbital, right? Oftentimes denoted by the topology of that orbital as, say, a sigma bonding orbital. And as a result, you also generate an antibonding orbital, right? Often denoted sigma star. Now this is very simple. This is in the case of hydrogen, right? But to a first approximation, the same kind of idea can be thought about here. Now, the amine-based orbitals that are interacting with these two orbitals reside much lower in energy to start out with. And so what happens when instead of combining H with another H, I instead combine it with something like a chloride ion? Right? In this situation, I start out with a difference in initial energies, and I still get a bonding and anti-bonding set. But of course, because this bonding set of orbitals, or bonding orbital, is closer in energy to the parent orbital that it started from, it has a lot more character of, if say this was a chloride atom, rather than having a significant contribution from the H, and likewise the anti-bonding has a significant contribution from here, and much less so from there. So if I'm going to tell you a priori that the nitrogen orbitals reside down here, and they interact with these orbitals here, what will that cause these orbitals to do in the resulting configuration? They'll move up in energy, right? Because they're the anti-bonding orbitals. So what basically happens, right, is that the interaction of these orbitals leads to a bonding and an anti-bonding set. The bonding set I'm not depicting here because it's not metal-centered. It's rather ligand-centered, but that would reside down here. And the antibonding combination exists with this dz squared and x squared minus y squared, and that antibonding combination raises the energy of this relative to the parent orbitals that they come from. This picture makes sense, right? All we're really doing here is taking what we learned in sort of freshman chemistry with regard to the bonding of simple atoms and applying it to a more complicated picture of the bonding of many ligands to a certain metal center. Okay. If you understand this very basic picture, this actually gets you very, very far in terms of understanding the reactivity and spectroscopy and properties of transition metal coordination compounds. Because by and large, the ordering of these d orbitals, and of course that will change as I change the ligands and change the environment and change the geometry, can predict for you a lot about the reactivity of this complex as well as its spectroscopic properties. We're going to walk through that over the next few minutes in detail. Right? One characteristic feature, okay, so first off, let's ask some simple questions. Right? How many electrons are going to populate this set of 5 orbitals for this complex? Cobalt hexaamine 2+. How would we go about answering that question? So the first thing we need to assess is what is the oxidation state of the cobalt center, right? And what is the oxidation state of the cobalt center? 2+, right? Okay, this is not a trick question. It's just that we have 2+ overall, and all of the ligands are neutral, and as a result, that charge is carried by the transition metal center. So this is a cobalt 2+ center. How many d electrons are there in a cobalt 2+ center? Where is cobalt in the periodic table?
The D block.
It is in the D block. But more importantly, how far to the right is it in the D block?
This is a special ones that like Yeah. But it's
No,
like
7
4
you would-
over 7.
7, so someone said 7, right? So cobalt is in, so cobalt, so when you have a cobalt, cobalt in the 0 oxidation state, you're in group 9, and the cobalt 2 is 2 less than that. So that leads to 7 residual electrons residing in the cobalt. So if I know that cobalt 2 is D7, how do I populate them in this arrangement? Is there only one configuration in which I can populate those electrons, or are there multiple? So I can populate them where all of them are spin paired, or I can populate them where some of them are not spin paired. That would correspond to either the high and low spin cases of the center, right? If I were to oxidize the cobalt to 3+, and I can certainly do that, then it would be D6, right? Rather than D7. So then similarly, whether it's low or high spin, I would get different configurations. Okay. So what will determine, right, the relative splitting of this and whether or not the electrons choose to pair up or unpair when they fill these orbitals has to do with the splitting of these orbitals, right? Because there's an energy unfavorability to having the electrons pair up. It's called a pairing energy, in fact. And so if the energy separation here is very, very large, then promoting an electron here versus pairing it up strongly would favor the pairing. Whereas if this is not raised that much up in energy, having it be unpaired and at a higher energy is more facile than having it be paired up. And so the splitting in these orbitals determines to a great extent whether you have a low or a high spin configuration. Okay. So let's consider for a moment what are the factors that give rise to either a low splitting between the non-bonding d orbitals and those anti-bonding orbitals. So that splitting is usually referred to as a delta knot or a 10dq or a ligand field splitting parameter. All of those are sort of synonymous terms. But this is strongly dependent on what we term the field strength, right? The ligands impose a field in terms of the electrons that are interacting with the electrons of the metal center, and the magnitude of that field is going to augment the separation of these orbitals. So there are classes of ligands that give rise to variation in this delta O, or this octahedral splitting parameter. And first, let's consider a situation where the ligands are only donating sigma orbitals. So an amine is a great example, right? The only orbitals that are in play in terms of interacting with the metal center is that orbital that's in that lone pair of the ammonia molecule, right? And that lone pair of the ammonia molecule is what's interacting with the d orbitals, and that's a sigma bonding interaction because it is cylindrically symmetric around the bond axis, which is between the metal and the ligand. But that's not the only type of interaction you can have, right? You can also have a situation where there's not only sigma contributions to that bonding, but there's also pi contributions. And let me explain what that means, right? So when I have the interaction of a metal center and, say, the ammonia molecule, the orbital interaction is with this lone pair, if you will, and whatever the d orbital at the metal center may be, and this is a sigma bonding interaction. But if instead this was, say, a chloride ligand, not only do I have a p orbital that can interact here, I also have an orthogonal p orbital. And that orthogonal p orbital can now interact with different orbitals on the transition. And as a result, you have not only sigma donation to the orbital, but also pi donation. And importantly, right, this p orbital that's interacting is now no longer interacting with the dz squared and dx squared minus y squared, but is rather interacting with those other orbitals that also point their orbital density in between the axes of the ligands. And this causes those orbitals to be raised in energy because they take on anti-bonding character. right? Just like the ligands would bond to make sigma bonds and sigma antibonds, these are, if you will, pi antibonds. The other possibility, of course, is that I have a ligand that has a very high-lying acceptor orbital, right? And in this case, the electrons are actually being pulled away from the metal center, and so these pi orbitals on the metal, the dxz, yz, and xy, take on pi bonding character, and they give rise to, at a higher energy, a pi antibonding orbital. Does someone know a ligand that might give rise to this pi acceptor character? One common ligand that gives rise to this is the carbon monoxide ligand. CO is a very common ligand for transition metal centers, and one of the reasons that it acts as a very good pi acceptor is because that carbon oxygen now has itself a pi star orbital that is high in energy and can accept electron density from the metal center, generating a bonding and an antibonding set, and that bonding set gives rise to pi bonding character here for the metal-based orbitals. So what you want to take as the upshot of all of this, right, is that depending upon the nature of the ligands, the field strength will be dramatically altered. Okay, so the key reason we're learning all about this, right, is that really the ligand field splitting of a transition metal defines so many properties of how that metal center actually gives rise to reactivity. So it defines everything from the color, right? I mean, take a look at this, right? Based upon different metal ions in a variety of different oxidation states, you can get a whole range of different colors. And the primary reason for that is that these colors are due to transitions of electrons between those orbitals in the d set. And so it gives rise to the color, it gives rise to the magnetic properties of these metal ions, whether they either repel or attract a magnetic field. It gives rise to their reactivity, the rates at which ligands substitute on them. It gives rise to whether or not they're very, very oxidizing or very, very reducing. And also it gives rise fundamentally to life, right? Many of the key functions in our body are provided by metal centers that are in the active sites of enzymes. And as a result, those metal centers give rise to get their reactivity from the ligand field properties in their environment. So this is really so central to so much of what we understand in both inorganic chemistry and chemistry more broadly. So how can we rationalize this, right? So there are some characteristic features that give rise to variation in the ligand field strength, and this is known broadly as a spectrochemical series. What the spectrochemical series is generally a measurement of, when you measure the overlap of a certain orbital, and the energetic match between the metal and the ligand, what you find is that some ligands engender a much higher split than other ligands, and this allows you to broadly categorize the extent of that ligand field splitting based upon the type of ligand. Let me just give you a representative example, right? So what we're doing in both of these columns is keeping the metal identity the same, right? So it's vanadium here, it's vanadium here, it's vanadium here, it's vanadium here. We haven't changed the metal center. All we've done here is change the ligands that are on the metal center. And remember, I told you before that something like chloride can both be a sigma donor as well as a pi donor, and that pi donation shrinks the separation between those d orbitals. And as a result, what you have here is a significantly smaller octahedral splitting. If you have a fluoride ligand, that does so less effectively, and so you get a larger splitting, and if you have just sigma donation from water, you get a fairly large octahedral split. Likewise, if you have, say, a cyanide molecule, right, something that's a good pi acceptor, that lowers that dxz, yz, and xy orbitals, and that increases the octahedral splitting. And so cyanide is denoted as a very strong field ligand because it gives rise to a large gap. Chloride, a comparatively weak field ligand, because it gives rise to a small gap. And water somewhere in between. The same can be found if you even change the transition metal center. Now obviously, the change in the metal center leads to a difference in the splitting for a given set of ligands. That's maybe not too surprising because it's a different metal. But amongst that metal, if you do the same comparison, you find a very, very similar trend. Something that is pi donating will have a much smaller splitting versus something that's significantly pi accepting will have a very, very strong and very, very splitting. Okay. So what this gives rise to is essentially a spectrochemical series where very, very weak field ligands are represented here. These are ones that are strong sigma donors as well as pi donors, both of which causing a small separation. And you go eventually to things that are just sigma donors like water and ammonia, and then very, very strong sigma donors as well as very strong pi accepting ligands. And all of this leads to a very, very large splitting. So metal nitrosyl complexes have very, very large splittings in general. And so you can broadly characterize these in this way. Here are all of your pi donor ligands, here are sigma only ligands, and here are significant pi acceptors. Now, what we looked at before was the magnitude of that octahedral splitting as a function of the type of the ligand. But I not only kept the metal center the same, I also kept the metal center's oxidation state the same. Right? And the variation of the metal center's oxidation state will also change the magnitude of the ligand field splitting, right? Because it will change the size of the metal ion and change the interaction of the metal centered orbitals with the ligand. And so what is the general trend, right? So for any given metal center, if you increase the oxidation state, make it more oxidized, what you will generally do is decrease the separation between the metal and the ligand. In other words, you can think about it as the metal ion is contracting as you increase its oxidation state, that pulls the ligands in, and by virtue of the ligands being pulled in, this leads to a greater overlap between the metal and the ligand, and that in net leads to a significantly higher splitting. Right? So if you think through this general logical train, here's some data to illustrate the effect, right? So here I'm preserving the ligand and the metal center the same, I'm simply varying the oxidation state. So if I start here with the chromium hexaqual compound in the 2+ oxidation state, you see a comparatively small ligand field splitting. If I oxidize by 1 electron, I get a significantly higher ligand field splitting, and that's because the waters are now closer to the chromium center and are able to push those orbitals up higher in energy. Same can be seen for vanadium. As you increase the oxidation state, the ligand field splitting increases significantly. Same can be seen for the cobalt case. Okay, so we know that both the identity of the ligand as well as the type of the oxidation state, as well as the donor characteristics of the ligand help to define this octahedral splitting. The other thing that's characteristic, of course, is some broad trends across the periodic table, which is that in general, first row transition metals exhibit significantly smaller splittings than their second row analogs, and those are roughly comparable to those of third row transition metals. The reason for this, right, is that the radial extension of the orbitals in the second and third row is significantly higher than that of the first row, and as a result of that, the metal-ligand bonding is much stronger. Because it's much stronger, that leads to a much larger separation of the d orbitals, and that gives rise to a larger split. And here's some examples to kind of illustrate this. So what we've done here is kept the oxidation state the same and the ligands the same, and all we've done is walk down one row of the periodic table. So we're going from cobalt-3 to rhodium-3 to iridium-3, and what you see is this systematic rise, with the most dramatic of rises actually occurring in these two essentially. Why does this all matter, right? Well, this all matters because this ligand field splitting and the nature of the bonding between the metal and ligand defines to a large extent the rate at which the ligands exchange on the metal center. And the variation is dramatic, right? We're talking about here certain metal centers like gadolinium-3, which will exchange. So what you're looking at in this plot is the rate at which a water molecule in the metal center will swap out for another water molecule. So it's an exchange reaction, one water for another water, right? And you're measuring the time scale, or the rate constant, or you can also look at it as the lifetime, right? The lifetime, the time, average time that a water molecule spends bound to that metal before it swaps off with another one. And you can see that if you have something like gadolinium, by the way, gadolinium is used as a contrast agent when you get an MRI. And the reason for that is that it exchanges waters extraordinarily rapidly. That means a very, very small amount of gadolinium will make a change in the behavior of the water through a large number of your cells and tissues. This is why gadolinium is used as an MRI contrast agent. And exchanges ligands on the order of 10 to the 10th. So the lifetime of a water molecule is very, very small, on the order of 10 to the minus 10 seconds on that gadolinium atom. Whereas you can find things like iridium-3 that exchanges extraordinarily slow, right? That's 20 orders of magnitude we're talking about here between the fastest exchange that we know about and the slowest exchange we know about. The variation is dramatic, right? And this is all reflected by some basic properties of the ligand field chemistry. I mean, let's take some examples here, right? So ruthenium-2 versus ruthenium-3, right? So we said that as you increase the oxidation state, that pulls the ligands in closer together and increases that splitting. As a result of those things being pulled closer together, the metal-ligand bonding is stronger. And as a result of that, the rate of the exchange is slower. And as a result, you see about several orders of magnitude, I think it's about 4 here, between the ruthenium-2 and the ruthenium-3, consistent with the bonding here being significantly stronger. And you can find this in a number of other places. Look at iron-3 versus iron-2. Again, several orders of magnitude here. Should be cobalt-2 and 3. I see the 2, but I don't see the 3 here. So anyways, a lot of examples here. Here's another good one. Chromium-3 and chromium-2. It's kind of amazing, right? We've moved 1 electron out, and we've varied now by about 16 orders of magnitude. It's actually very interesting because the chromium-2 and chromium-3 were exactly the system that Henry Talby first studied to be able to understand the rates of ligand substitution of metals. And what he understood was that when you exchange an electron between a chromium-2 center and a chromium-3 center, by virtue of the fact that this is so inert and this is so labile, it turns out actually that when the electron gets exchanged, the ligand exchanges simultaneously. And this became a whole field known as understanding inner sphere charge transfer reactions. It's something that my own group studies today in a different context, but has really set the stage for about 50 years of exploration in this field. Okay, so what I told you about a little bit is sort of the rates of ligand substitution. What we're going to spend the next little bit is discussing actually what are the mechanistic pathways for ligand dissociation. So there are different ways you can substitute a ligand. Say, for example, you have a pentamine cobalt center, and say that the way it substitutes is by first having one of the ligands pop off. Right? This is possible. And then you can have another rate at which a new ligand comes in. Now, if this were in fact the case, and I tell you that in a mechanistic model I say this is what's limiting the rate, whereas this is fast, we can put together a rate expression. So what would be the rate expression for this process? If you wanted to write a rate law for this reaction, how would you do it? Well, you have to ask yourself, what is the rate limiting process? And what is the species that's participating in that rate limiting step? And as a result, right, you would say, well, the velocity of this reaction will be given by a rate constant K1 for this rate limiting step. And it will be multiplied then by the concentration of the species participating in that rate limiting step. And this is the type of rate expression you get. By the way, I see a lot of you furiously writing notes. We're going to have all the slides for you later, so just pay attention, right? Now, what would you expect, right? What if you make the L, or the ligand here, the new one coming in, significantly more nucleophilic? In other words, I make the rate of K2 significantly increase. Will that affect the overall rate? No, right? Because this is not limiting the rate. I can increase this dramatically. The only thing that is governing the rate here is the rate of dissociation of this ligand. And that's why we call this dissociative ligand substitution. It refers to the type of mechanism by which this occurs. Okay, now let's consider a different possibility, right? A situation where we first have the ligand dissociate, but we have a different type of mechanism. We have it so that this dissociates in quasi-equilibrium. Some of it pops off, some of it comes back on, some of it pops off, some of it comes back on, but this happens many, many, many millions of times, let's just say, before a new one comes in. What would be the rate expression here? So we start, as we always do, and we ask, what are the species participating in the rate limiting step? Right? So the velocity of this reaction now is given by the rate constant K2 But now, not only the concentration is intermediate, but you also have to multiply by the concentration of the new incoming ligand, right? Because this is a bimolecular reaction. I have to have a ligand meet up with this metal center. As a result, there's a dependence both on the concentration of metal, as well as a dependence on the concentration of the ligand. And the multiplicative of those two is what's giving rise to the overall rate. So we get a rate expression that looks basically like this. But remember, this is a transient intermediate. We're not actually able to observe this, nor are we able to measure this. And we certainly don't know a priori what the position of this equilibrium is. So we can use the steady state approximation. What that basically says is that whatever the concentration of the species is, it's going to be invariant with time. As a result, the rate of its formation should equal the rate of its elimination, and it's formed by K1, and it's removed by K minus 1 and K2, and so you get this overall rate expression. If you rearrange terms here, you can essentially determine an expression that will rewrite this in terms of the concentration of species you know, like the cobalt hexamine, and the relevant rate constants. And if you put these two together, what you'll find is that the overall rate is now governed by the K1, the K2, as well as this K minus 1, and K2 times L. And in the limit, right, in the limit that you have a situation that the rate constant for K2 times L is significantly smaller than the rate constant than this expression here, right? Then you can make an approximation, because I said this is rate limiting, right? As a result, K2 should be fairly small relative to either of these. We can eliminate this term from the expression, and what this will reduce to is a big K1, or the equilibrium constant for this reaction, and it will be dependent in an inverse fashion on the concentration of the ammonia. But this is not surprising to our intuition, right? Because in this step, ammonia is being liberated. So if I add more ammonia, I'm going to push this equilibrium. I'm going to Le Chatelier this over to this side. As a result, I'm going to inhibit the rate of the overall reaction. Okay. How would we distinguish this from the previous case? Right, the way we distinguish this from the previous case, right, is to be able to understand the dependence on the ammonia and what other factor. Remember before we said there would be no dependence on the nucleophilicity of the incoming ligand. Is that still the case here? No, right? Here there would be a strong dependence on the nucleophilicity of the incoming ligand because that's directly involved in this rate expression. It is even there in the resulting rate expression. So by varying those parameters, we can determine which of these is actually the viable rate. This is not the only mode in which you can do this reaction. You can also do a different type of ligand substitution, an associative ligand substitution. Sorry, that should be associative here. And in this case, you can envision a rate-limiting step where you actually have a ligand binding, right? And in this sequence, what would you get for the rate expression? You get a rate expression that looks essentially like the ligand incoming times the concentration of the species. Again, what if we make the ligand a lot more nucleophilic? We find that we would lead to a strong rate enhancement because now we're gated by the rate of that new incoming ligand binding to the metal center, and not gated by the dissociation of a ligand that's already bound from the metal center. Now, let's come a little bit full circle, right? One of the things that Arrhenius discovered was that activations or the rates of reactions were strongly dependent on temperature. So if, for example, we have the rate of substitution of this cobalt center, we have not yet discussed a lot about what defines this rate constant. And this rate constant is given by the activation barrier for this reaction over a thermal parameter RT, right? And a collisional prefactor. So this is essentially the rate or the frequency by which molecules come together, but not every one of those molecular collisions is going to be productive, or if you will, the rate of thermal activation is, but what is going to define the barrier is the activation for the dissociation of this reaction. And what you can do is take this Arrhenius type expression for the rate constant and turn it into a logarithmic form. By taking that expression in a natural log, what you find is that you should get a very, very clean dependence between the natural log of the rate constant and 1 over temperature. Right? And so this is a way to actually understand and determine the activation parameters for a given reaction. What could cause this plot to be nonlinear? Now, when we change the temperature, right, we're changing fundamentally the value of this rate constant. What if we change the rate constant so much that after a certain time, a different step in the mechanism becomes rate limiting? So there's no guarantee that over the entire temperature range we would probe, we necessarily have the exact same mechanistic sequence. And if at some point the mechanism changes, that would alter the profile of this plot. So there are situations where this plot can be nonlinear. So in the last few minutes, I want to finish off with a little bit of understanding of the techniques that you're going to use. One of the really powerful ones for determining rates is to determine the kinetics by UV-Vis spectroscopy. And so what are the actual axes of a UV-Vis spectrum? What you basically have is a data readout that has absorbance on one axis and wavelength on the other axis, right? So we're looking at the transitions that exist in a molecule as a function of that. And the question you can ask is, what fundamentally is absorbance? It's a very interesting term, right? What absorbance really is the ratios, and so you can understand this a little bit by looking at how your spectrometer is actually working. You have two lamps. The lamps go to a mirror. Then this produces basically a broad spectrum of light. That broad spectrum of light is put through a filter to select out a single color or a single very narrow band of energy. That band of energy then goes to a beam splitter and a reference sample relative to the sample you wish to measure. And what you're measuring is the relative transmittance of light in your sample relative to the reference. And if you have those two values, what you get is an intensity of light versus an intensity of light sub-zero, which is related to the reference. And the absorbance is simply the negative log of that transmission. And that transmission of light is simply the direct ratio of I over I0. Right, so this is really what absorbance is, and this is what the spectrometer is actually producing for you. And the reason we do this, right, is that if you plot data in absorbance, you find that the absorbance is linearly related to the concentration. This is what's known as the Beer-Lambert law or Beer's law. And this constant is known as the molar absorptivity. It is an intrinsic parameter of a given molecule. And you can see the units here, it's in reciprocal molar, reciprocal centimeter. And the reason is that absorbance is this times the product of the concentration in molarity and the path length. The path length of a usual UV-Vis cell is 1 centimeter. And as a result of that, this becomes a unitless absorbance, right? And the reason it's unitless, right, is when you take a log of a particular number, it becomes unitless, right? And that's what that is. It's the log of the transmittance, right? So when is this law valid? It's valid when you have dilute solutions, because if you have a very concentrated solution, the amount of light you may be absorbing may be very high, and so your power to discriminate variation in that I versus I0 is small. And so Beer-Lambert law will deviate. You also need a homogeneous solution, because if the solution is not homogeneous, you will not only absorb the light, but you also scatter the light. And light scattering is not the same as absorption, and the dependence on the two are very, very different, both in terms of wavelength. In fact, scattering has a very characteristic 1 over lambda to the 4th term. This is known as Rayleigh scattering. This is why the sky is blue, right? That's a different process than absorption. And that there are no concentration-dependent reactions, right? So what I'm saying is that the absorbance is going to be linear in variation in the concentration. Of course, this won't hold true if when I raise the concentration to a high level, the molecules dimerize or react with each other, because then obviously the product of that reaction will have a different absorption. So these are some of the key criteria that are necessary for this to all be the same. And if in fact all of this is true, you can replot any UV-Vis spectrum in terms of the intrinsic properties of the molecule, essentially convert that absorption with the known concentration into a plot of extinction, right? And this extinction is now this molar absorptivity as a function of either the nanometers or wave numbers. This is just an energy unit versus a wavelength unit. And this is an example of, say, a cobalt-2 ion. And this gives you intrinsic information about the concentration of species in solution and their molecular properties in terms of the likelihood of absorbing that. Okay, so this is all I have for you today. What I've kind of tried to give you is an overview of kind of how we think about the reactivity of transition metal compounds, and in particular how we use that to understand the kinetics of their substitution reactions, And that's really kind of what will be the focus of most of the work that you do in this lab, both from the synthetic side as well as the kinetic side. So with that, I'd be happy to, of course, take any questions, and I hope you have an enjoyable module. Okay, great.